Okay, everybody, we're here for 11.4 logarithms. You did logs last year in advanced algebra, and it's a really big topic to understand the opposite or the inverse operation of exponentials. So we're going to be talking about how do you go back and forth between exponentials, which we've been working with, and log, and then also some of the properties of log and what the graph looks like when you do the opposite or the inverse operation. So we're going to walk through some of these basic properties. So in exponential world, I'm going to write it a little bit differently, but we have always a base being raised to a power, and we get a number for our answer. So I'll just call that b to the p equals n. So b for base, p for power, and n is the number you get for your answer. In log version, we have a little bit different way of writing that. So the log base b of a number is equal to a power. So the b is a subscript, and the log is equal to the power of the exponent. So a really powerful thing to think about is really logs are exponents. So I'm going to show you an example to see what I mean to go back and forth. So I'll write a statement that we know to be true. So 3 squared equals 9. That's an exponential equation. So 3 is the base raised to a power of 2 equals 9. What would that look like in log form? Well, if you rewrite it, it would be log, and then your base from the exponential was a 3. Of what number? Well, what number did we get for our answer? Well, that was 9. So log base 3 of 9 equals whatever that exponent or power was, which is 2. So really, when you think about it, what the log is asking you is 3 to what power gives me 9 when you see that statement. So it's kind of like going around the circle when I rewrite it. I like to think of it that way. So log base 3 of 9 equals 2. And going backwards, it's the same thing. You can say 3 to the second power equals 9. So I kind of like that circular idea to think about how that goes back and forth. So they're really two different statements saying the same thing. They're inverses, just like multiply and divide. 3 times 2 equals 6. 6 divided by 3 is 2. It still kind of works the same way. All right, so here's just the example from your book then, the definition. So the log function, y equals log base a of x, where a has to be greater than 0, so the bases are positive, and they can't be 1, because that wouldn't be very exciting. 1 to a power, it's always 1, is the inverse of the exponential y equals a to the x. So we have that back and forth idea. So they have just another example here to show you 2 to the y equals 32. That means log base 2 of 32 would be equal to y, going back and forth. So a couple things to keep in mind, some important points. Logs are exponents. So when we're working with them, it's the power that's being raised to that expression. So logs are exponents. So they behave in the same way. They follow the same exponent rules. And the inverse of a log is an exponential. So it's the inverse of an exponential. So those are the two kind of big things to keep in mind when we talk about logs. Oops. All right, so let's get into some examples first of all in terms of what the graphs look like when we talk about these log statements, and also just rewriting back and forth. So having you practice kind of what that statement means, then we'll get into the graphs. All right, so it says write the equation log base e of 13.7 equals x in exponential form. So your base is e, the number is 13.7, and then the power you get is your x. So when you rewrite this, it would be the base e raised to what power x will give you the answer 13.7. So think about that circle idea I talked about before. E to what power equals that for an answer. That would be exponential form. Two different ways of saying the same thing. Okay, let's go the other direction. True statement. A base, so 1/4, being raised to a power -4 is giving you this number for your answer. Remember what negative exponent means? Flip, so it's like 4 to the 4th. So what would that look like in log? Well, it would be log base 1/4, so that's a subscript, of the number 256 equals, okay, when you think about just what that statement looks, it's asking you 1/4 raised to what power gives you 256? Well, what power? It's always the log, is -4. So again, that circle idea, that helps you. So base of what number equals the power, that -4. So that would be the log version of it. So just going back and forth. So it's a big idea is being able to convert back and forth. Okay, let's take a look at the graphs. What I did is I graphed 2 to the x, which we started out with in our last sections. And that's the graph that you see in blue here on the video. I know yours isn't blue, but I'm going to make mine blue. So that's y equals 2 to the x. Now, if you want to do the inverse, we want to rewrite that as a log statement. So I'm going to kind of walk through kind of that process of how would you convert that into log. If you want to find the inverse equation, see if you remember way back from chapter 1, how do you find the inverse of an equation? Think for a moment. We take the x and y, the domain and range, and flip them, and then solve for y. So I'm going to go ahead and do that. So I'm going to take my original equation, which is this, y equals 2 to the x, and I'm going to switch the domain and the range. Then I'm going to solve for y. So to do that, we have to take that statement that we just had, and we're going to rewrite it as a log. So if I rewrite that as a log statement, it would be log base is 2 of what number? X is equal to the exponent of the power y. And that's that inverse statement that we're getting down here. So we're just rewriting it. So that's that same inverse. So log base 2. So remember what happens to the domain and range? They split, or they switch. So the domain of the original function, the blue one, 2 to the x, is all real numbers. You can pick anything you want. But the range has to be greater than 0. We talked about that asymptote. Well, if you switch those, that means the domain then has to be bigger than 0. So we have a vertical asymptote down there. Can't ever go to the left of the y-axis. And then the range is all real numbers, so it keeps growing. So if you look at your inverse there, the inverse equation is the red one on the video. So if you literally take the ordered pairs, and we'll do that in a little bit, and just switch them. So for example, a point on our original graph would be 0, 1. All exponentials have 0, 1 as their y-intercept. Well, that means you would have to have the point then on your inverse. That would be 1, 0, which is right here. And you can do that for all the points on that graph. All right, so that's our picture and our relationship between the two of them. And if you remember the symmetry they have, this little green dashed line in here, what symmetry does a graph always have with its inverse? Y equals x. So that line y equals x. So that same symmetry is true when we're looking at that relationship with log. All right, so let's take a look and do a graph then so you can get that picture. It's really hard for people to graph log without really thinking of the exponential equation first. So some people do that and just flip it. But here's what I do. I just rewrite in an exponential statement, because for me that's easier to do graphing when I'm looking at it written as an exponential. So I'm going to rewrite this in exponential form. So my base is 5 raised to the y power equals x. Now, that's not really super convenient to solve that for y, but what I can do instead, just to kind of plug these numbers in, this is the inverse of 5 to the x, so I could graph 5 to the x and switch all the ordered pairs. Otherwise, I'm just going to think of it as, I'm going to plug in the numbers for y. That would be a lot easier to do. So I'm going to substitute in numbers for y, because when I plug them in, it's going to be faster to deal with. So 5 to the negative first, that would be 1/5. 5 to the 0, that would be 1. And then 5 to the first, that would be 5. And go ahead and plot those points. So if the y is negative 1, we've got 1/5. If y is 0, we have 1. I know it's kind of backwards. And if y is 1, we have 5. So your asymptote, remember, is the negative y-axis, and you're going to get a graph that looks something like, gotta get closer and closer there, something like that. So it's pretty steep because the base is 5. That would be the inverse, remember, of 5 to the x. So the inverse of 0, 1, 1, 5, and negative 1, 1/5. So if you put your original graph, this would be y equals 5 to the x. Its inverse would be y equals log base 5 of x. So for me, if I'm going to make a sketch, you can think of it either way. And again, it has that nice symmetry through our y equals x. So it's going to fold over that. So that might be an easy way to think about what those graphs look like. Okay, let's talk about some properties that are always true for logs. This is important to recognize when we go through and simplify. There's basically all the different exponent rules that we do for regular exponents work for logs. But the first one I want to talk about is sort of a basic idea. It's called the equality property. It says if two logs are equal, and notice their bases have to be the same, if two log expressions are equal, then the expressions on the inside must be equal as well. It's kind of one of those duh properties, but it makes sense. So I'm going to go ahead and give you an example. So log base 2 of x equals log base 2 of 5. If this was a statement that you were to see, the bases are the same, they're both 2, the logs are equal, so what must be true? Well, the stuff on the inside then would have to be equal as well. So that value of x would have to be 5. It's a great way to be able to solve and put things together. So we'll use the equality property a lot. The next one's called the product property. Think of what you do with exponents. When you multiply two things with the same base, you add the exponents. That's a regular exponent rule, property. Well, this is the same thing. Logs are exponents. So this is saying the log of a product, m times n, that's your product in there. That's where this name comes from, is equal to the sum of their logs. So the log of m plus the log of n. So if you have it written as a sum, you can rewrite it back as a product. Or if it's written as a product, you can break it apart. Let me give you an example of something like that. So I have the log base 7 of 15 equals the log base 7 of 5 plus the log base 7 of x. Okay, so kind of working backwards, let's see what we've got going on here. On the one side of the equation, we have a sum of two logs, log of base 7 of 5 plus log of base 7 of x. We know from the property right above that that's equal to the log of the product of those two values. So I could write this as the log base 7 of 5 times x. That's using the property. So the sum of two logs is the log of the product. Well, how does that help you? Well, look at the other side of the statement then. Now you have equality, two logs that have the same base. So I can set the expressions on the inside equal as well. So 15 would have to be 5x, so x would have to be 3. So thinking about what those properties would do for us, we can solve for a lot of pieces. All right, let's try two more. Quotient. A rule for quotient is if you divide two things with the same base, you subtract the exponents, and that's where this one comes from. So we have division over here is equal to the difference of those two logs. And again, notice all the bases are the same. All right, so let's give an example of that. So if you had log base 4 of 3 equals log base 4 of 12 minus log base 4 of x, how could we use that property to simplify? Well, on the side over here with the subtraction, the difference between those two logs, since the bases are the same, we could say the log base 4 of 12 divided by x. And again, because we have this equality property as well, with the same, that same base, both of these expressions would have to be equal because the logs are equal, their bases are the same. So we get an equation 3 equals 12 over x. What would x have to be? Cross multiply, divide, 3x equals 12, so x must be 4. So you can do a lot with solving with all of these. All right, last one, power property, and then we're going to practice these a little bit. The power property has to do with the power to a power rule. So if you had like x squared cubed, what do you do with the exponents? Well, you multiply them. So that's what this is saying. You are multiplying the powers together. So remember, log is an exponent, and so is the p. So when you multiply them together, that's that product property. So basically, in effect, it's saying if something on the inside is raised to a power, you can bring that power out front as well. How might that help you? Let's take a look at an example. So 2 logs base 6 of x equals the log base 6 of 49. Okay, let's look at the left-hand side here. The number 2 is out front. It's written as a product, so that's like this side of the property. So where else could that 2 go? Well, it can be up here as an exponent. So log base 6 of x squared now equals log base 6 of 49. Why might that help us? Well, now we have equality. If there's a number out front, we don't, but now we do. We have 2 logs that are equal with the same base, so the expressions on the inside must be equal. So that means x squared equals 49, or x equals, now when you square root, technically plus or minus 7, right? Okay, I want to direct your attention back to the graph. The domain for log is all the x's that are greater than 0. Okay, so let's go back to our example then. Would we be able to put a negative 7 back in for x here? Well, no, because 6 to no power is going to give you a negative 7. That's impossible. It's not going to work. So the only one that actually makes sense is just the 7. So we do have to keep that domain in mind as we're working through these. Okay, so how does that help us? Let's take a look at some examples here. It says evaluate the expression. So using these log properties. There's a couple different ways to do this one. When you have a log statement like that where there's nothing equal to on the other side, my inclination is to go ahead and set it equal to something, call it something, so you can rewrite it. and work with it. So I'm going to use the method of rewriting this as an exponential. If you have a log statement, sometimes rewriting it as an exponential really helps to have you go through and solve. So I'm going to go ahead and rewrite it as an exponential. So the base is 4 raised to the x power would have to be 4 to the third. It has to be that number. Well, if the bases are equal, then the exponents have to be equal as well. So 4 to what power would be 4 to the third? Well, x would sure have to be 3, wouldn't it? Now, that's one way to do it. Here's another option, though, which I kind of like. You don't have to set it really equal to anything. I just want you to use that power property. Where else could this 3 go? Well, it could be down front. So you could have 3 times the log base 4 of 4. All right, now let's talk about this part right here. Log base 4 of 4 means, just kind of off to the side here, log base 4 of 4. Let's set that equal to something. That means 4 to what power would give you 4? Well, 1, right? So 4 to the first would be 4. So anytime the base and the number are the same, that has to be 1. Log base 4 of 4 would be 1. So would log base 10 of 10 or log base 15 of 15. So that whole guy equals 1. So then what you have is 3 times 1, or 3. You can get the same answer in a lot of different ways using those log properties. All right, see if we can use log properties on the next one to help us solve too. We have a sum over here, and if you look back, the sum of two logs at the same base is the same as the log of the product. So that would be log base 2, and I'm going to write the 10 first because that just looks better to me, and then log base 2 of 70. So now we have our equality property, so what's inside has to be the same as well. So 10x would have to be 70. So x would be 7. So it's a nice way to go ahead and solve. So just recognizing and being able to do that. All right, let's try one more of these. We've got a whole bunch of stuff going on here. So see those numbers out front, order of operations, deal with the multiply before the subtract. We need to deal with these exponents, so we're going to bring them up top. They're going to be the powers on the inside. So log base 5 of 4 to the third minus log base 5 of 27 to the 1/3 equals log base 5 of x. Okay, now we have a difference of two logs at the same base. That's the same as the log of the quotient. So those two things divided. All right, now we have our equality property. We have two logs that are equal. Their bases are the same. So the stuff on the inside better be the same as well. So 4 to the third is 64. Cube root of 27 is 3. So x must be 64 over 3, whatever that value is. 21 to the third. You can leave it as an improper as well. So you can use all of these in conjunction with one another to help make life a little bit easier. Okay, so really quick, we're going to go through just some basic, just kind of check. Try these and then kind of pause the video as you go so you can try them first and then get the answer. For all of them that are just evaluate like this, I would set them equal to something to make it a little bit easier to think. But in your head, number 1 is 5 to what power? Give me 125. If you can figure it out, great. Otherwise, you can rewrite it. So 5 to the x equals 125. That's thinking 5 to what power gives you that? Well, what power of 5 is 125? That would be 3. So 5 to the third power, so the answer to the first one would be 3. So you're thinking to what power? So think of that for the second one, number 2. 3 to what power would give you 81? That's what log base 3 of 81 means. So if you rewrite it, 3 to the x equals 81. Think of what power of 3 81 is, and that's the fourth. So that's got to be 4. All right, next one. A little bit trickier. Log base 5 of 1 over 625. All right, let's see what we can do for that one. Let's do this one in red. So 5 to what power would give you 1 over 625? Okay, if it's in the bottom, think about it. What kind of an exponent is going to have to be if we need to flip? It's going to have to be a negative. So 5 to what power would give you 625, first of all? That would be fourth. And because it's in the bottom, negative. So that one would have to be negative 4. So exponents can be positive or negative, remember. Or, like in number 4, let's see what happens here. Set that equal to x. 125 to what power would give you 25? This one's really tricky to figure out because you can't really just guess and check whole numbers. The answer isn't a whole number, but if you can write them both as powers or bases of 5, so 125 is 5 cubed, 25 is 5 squared. The bases are equal. Well, gosh, the exponents better be the same as well then. So this would have to be 3x equals 2, or x equals 2/3. And you can try it in your calculator, type it in. Do 125 raised to the 2/3, don't forget the parentheses. You're going to get 25. So let's take the cube root and then square it. So we get that value. Okay, the last one is just using the equality property. Number 5, the bases are already the same. There's no numbers out front, so I can just say, yep, the two inside expressions must be equal. So 2x plus 5 equals 5x minus 4, and solve for x. So x is on one side, numbers on the other, so x equals 3. So a really good application of those log properties. Okay, so for our last one, I just want to see if we can do kind of a half-life example to talk about what that might look like. So we have our half-life formula on your formula sheet there, which looks like this. Y equals y0, 0.5 to the t, so that unit of time. So it's taking half of something every whatever unit of time, depending on what that thing is. All right, so let's take a look at this one. It says, how long will it take for those initial amount of grams, so 256,000 grams, with a half-life of 25 days to decay down to 1,000 grams. So your final amount is only 1,000. Okay, well, let's see if we can figure out what this is going to look like here. And this is to the t power. All right, well, when we solve for something like this, you always want to get the exponential thing by itself first. So the very first thing I would do would be divide by this 256,000. We're going to be doing a lot more of this solving stuff over the next few days. And that gives us 1 over 256, I believe, equals 1/2 or 0.5 to the t. Okay, let's see if we can solve a little bit. Think about what we did before to make the bases the same. See if we can figure out what this would have to be. So if I'm going to rewrite this as an exponential, or think about what power that would have to be, how many of those cycles or half-lives we need to get down to 1,000. So I need to figure out what power this is. So 2 to what power will give you 256? Kind of doing my scratch work off to the side here. Well, I think that's 8, isn't it? So this would have to be to the 8th power. So t would have to be 8. So 1/2 to the 8th power will give you 1 over 256. So it would take 8 cycles or 8 half-lives for that to happen. And how long is a half-life? I think it was 25 days. So 25 days, 8 half-lives, that would give you about 200 days for that to happen. Now you could figure it out. You could just keep multiplying by 1/2 and see how long it took you to get down to 1,000. But the whole idea is that we would be able to use an exponential situation to help us solve for an equation. But that's just kind of a preview, I guess, of what you're going to see over the next couple of weeks. So the first thing I need you to really understand, though, is all those rules for exponents. So going back over the log properties and being able to go back and forth between exponentials and logs. So I have the assignment up here, so I'm going to let you kind of pause and you can take a look at this. So it's page 723. So we're going to be working on in class 20 through 52 even. So it looks like that, and I'm going to scroll down a little bit too so you can pause if you need to when you're working on this so you have the whole thing. And hopefully we'll get really great at logs.